Alright guys, your essential question for today is from section 1-2 on finding limits graphically and numerically. And the way we're going to start off today's subject is by giving an informal definition of what a limit is. The informal definition of a limit is if f of x, so if your function becomes very close to a single real number, let's call that L, as x approaches c from either side. So let's say there's c right here. If you approach it from either side, if from the left-hand side and the right-hand side it's approaching the same singular real number, then the limit of f of x as x approaches c is L. Notation-wise, we write that like this. The limit of f of x is L. The limit LIM as x approaches c of f of x is L. And if you notice, if I start on the outer edge, if I work my way inside on the left-hand side and on the right-hand side of c, you notice that it is approaching a single real number. That value is the limit. Alright, in order to calculate limits, there are three ways that we are going to focus on it. The first is numerically, which means we're going to construct a t-table and look at those values and try and estimate what the limit might be. Another way is graphically. We're going to be drawing graphs or looking at graphs and trying to determine whether or not there exists a limit. And then finally, the one that we're going to be doing tomorrow is the analytical approach, where you use algebra to calculate the limits. So we're going to save that for the next lesson. So let's go ahead and take a look at the first example. It says use the graph and complete the table to find the limit if it exists. Now notice that I do give you the graph of the function. So my function right here is x cubed. I want to find the limit of this function as x approaches 2. So I want to find what the value of my function is as x approaches 2 from the left-hand side and from the right-hand side. Well, if you look graphically, from the left-hand side, as you approach 2, it's approaching the value of 8. And if you approach it from the right-hand side, so from the right side of 2, it's also approaching 8. So you can very easily look at the graph and determine what the function is. But let's say I didn't give you the graph. Let's say I just gave you a t-table. One way that you could find the limit is pick values that are very close to that number on the left-hand side and numbers that are very close to it on the right-hand side. So if I want to find the limit as x approaches to 2, I'm going to pick numbers that are getting closer to 2 on the left-hand side and closer to 2 on the right-hand side. And what I'll do is I'll plug in each one of these values into my function and get a value. So for example, if I plug in 1.9 into x cubed, that's going to give me 6.859, or we'll just say 6.9. Yeah. Let me change this to 6.9. Okay, if I plug in 1.99, that'll give me 7.9. And if I plug in 1.999, that'll give me 7.988. So you notice that the value is getting closer and closer to 8. Well, let's try the right-hand side. If I plug in 2.1, that'll give me 9.3. If I plug in 2.01, that'll give me 8.12. If I plug in 2.001, that'll give me 8.012. So from the left-hand side and from the right-hand side, you notice that these numbers are approaching the number 8. So that would mean that the limit of x cubed as x approaches 2 would be 8. Again, we confirm that by looking at the graph. Now, this is very vital. It says if the function is continuous at the value of x, and it is continuous. In order for a function to be continuous, it's got to be approaching the same number, it's got to be defined, and it's got to be equal to what it's defined, and it satisfies all three of those conditions. It says the limit is easy to calculate with something called direct substitution. In other words, just simply plug in 2 into the function. 2 cubed is 8. And this is what we would consider an analytical approach. So all three methods are shown here, either graphically, numerically or analytically. And again, direct substitution only works if the function is continuous at that point. All right, let's take a look at another example. All right, for this one it says use the graph and complete the table to find the limit if it exists. Unfortunately, I'm not able to do direct substitution in this case because if I plug in -1 into this function, x squared minus 1 over x plus 1, that's going to give me -1 squared minus 1 over -1 plus 1. That's going to give me 1 minus 1 over 0. That's 0 over 0. That's indeterminate form, so the value at -1 is undefined. Now, what's interesting, guys, about the limit is not really concerned about whether or not it's defined at that point. It's only concerned about whether or not it's approaching the same value, or what is it approaching. So it wants me to find the limit as x approaches -1. So -1 is right here. And so if you notice, on the left-hand side, it's approaching -2. On the right-hand side, it's also approaching -2. So even though the function is not defined at -1, the limit does exist. The limit, it's approaching the same value on the left-hand side as the right-hand side. It's approaching -2. So even though we couldn't solve it analytically, we can prove it graphically and numerically. If I plug in each one of these values, so -1.1, -1.01, -1.001 into my function, and I plug in -0.999, -0.99, and -0.9. And notice, guys, the reason why I pick these numbers is I want numbers that are getting closer to -1 on the left-hand side and closer to -1 on the right-hand side. So that's where these numbers for the t-table are coming from. But if you plug these numbers in, I'm going to get -2.1, -2.01, -2.001. If I plug in these numbers, I get -1.999, -1.99, and -1.9. So as you can see, they are approaching the same number. They're approaching -2. Now, when we start doing the analytical approach, I will show you how you can, using algebra, prove that the limit is -2 with direct substitution. But for now, you don't know those methods, so you can't really do the analytical approach for this, but you can prove it numerically and graphically. All right, let's take a look at one more example. For example 3, it says use the graph and complete the table to find the limit if it exists. Now, again, I've given you the graph of this situation. This is what we call a piecewise function. The reason is because it's broken up into 3 pieces. It wants you to find the limit as x approaches -4 for the function, and here's the 3 pieces. You use 7 plus x when x is less than -4. You use -6 when x is -4, and you use -1 minus x when x is greater than -4. And this is a representation of that function. Notice that both of these are lines. X7 plus x, that would be this function right here. -6, that's this value right there, that point. And then -1 minus x, that's this function right there. So there's my function. If you notice, since I want to find the limit as x approaches -4, -4 is right here. And if you notice, the function is not defined right here. It's defined right here at -6. So the value at x equals -4 is -6 by looking at my graph and by using that chart. But what you want to notice is my graph approaching -6? The answer to that's no. It's not approaching -6. If you follow your graph, this part of the graph is approaching the number 3, and if you go to from the right-hand side, it's also approaching 3. So the limit in this case would actually be 3, because remember, the limit is not necessarily what it's defined at, it is what it is approaching. And so in this case, they're both approaching 3 from the left-hand side and to the right-hand side. Now, we can prove that using our t-table. Again, I picked numbers that are bigger than 4 and smaller than 4. So if you plug these values in, you'll get 2.9, you'll get 2.99, and you'll get 2.999. Looks like it's getting close to the 3 over there. And then over here, I'd have 2.9, 2.99, and 2.999. Again, it's approaching both sides. If you notice, it looks like they're approaching 3. Just for some odd reason, for this function, it's at -4, the value is -6. That doesn't matter. Again, if the function is not continuous at the value of x, the important thing, this is the important thing is what the output gets closer and closer to as x approaches the value. In other words, the limit is more concerned about what it's approaching than what it is actually at that point. Now, for these 3 examples, we talked about limits that do exist. For example, the first one, the limit existed simply by doing direct substitution. For the second one, the limit existed. You can look at the t-table because they're approaching the same number. And then the same one here, the limit existed because they're approaching the same number. But to finish up today's lesson, let's talk about 3 limits that fail to exist. And we're going to skip example 4. Yep, don't want it. All right, 3 limits that fail to exist. Here's the first one. If they approach different numbers on the right-hand side versus the left-hand side, the limit for that point does not exist. Now, I'm going to teach you later on about the difference between left-handed sided limits and right-sided limits, but for right now, if we're talking about a limit at a point, so like, for example, at the point -4, the limit would not exist because it's approaching 6 on the left and approaching 3 on the right, so that limit does not exist. Another time a limit would not exist is if it approaches infinity. So for example, it says f of x increases or decreasing without bound as x approaches 0. So for example, let's say I want you to find the limit for this function as x approaches 0. Well, in this case, 0 is right here. And so if I approach 0 from the left-hand side, it shoots off to negative infinity, not -8. It shoots off to negative infinity. If I try to approach 0 from the right-hand side, it shoots off to positive infinity. So it's increasing or decreasing without bounds. So in this case, the limit does not exist. The third final one is sometimes when you, especially if you have trigonometric functions, if your function oscillates between 2 fixed values. For example, right here, you can look at the t-table. The function is oscillating between -1 and 1, -1 and 1. So that limit does not exist. You can look at graphically. So like, for example, it looks like the limit exists, but then when you zoom in, it gets worse, and then when you zoom in even more, it gets worse. So that limit would not exist. So the 3 times the limit does not exist would be when they do not approach the same value, when they approach infinities, or when they are oscillating values. All right, that's it for today's lesson. If you need to go back and review it, by all means, hit the restart button.